Okay, today we're going to cover Chapter 30, Sections 5 through 6. So go read those concepts. There's a number of them, and come back and we'll apply those to these examples. Okay, concept question 8 is an escape speed question. Now there's an equation for escape speed, and you can just plug it in and do its proportionalities. But it is such a quick and beautiful example of conservation of energy. I want to start there. So the idea of escape speed is that you start at the surface of a planet with some initial speed, huge speed, very massive speed. Okay? And you also, since you're on the surface of the planet, have some potential energy. Okay? Then the goal is to have a big enough speed, but just barely big enough, so that when you're far, far away, that's U final, you're not moving. That means your K final is 0. Okay? So this is big enough to overcome that, such that when you're far, far away, you have no kinetic energy. So we can say that's 0 and that's 0. Far, far away means no interaction, no interaction energy. We're left with this. So subtracting Ui to the other side, we're left with 1/2 mv initial squared equals, remember, this is negative. So when you subtract the other side, you end up with an overall positive, Gmm over r squared. Okay? So masses cancel, which is interesting because it doesn't matter if it's a trash can or if it's a space shuttle. It's got the same initial speed necessary to get out of the interaction of the Earth. Now, the reason why that seems totally wrong is because that's not how we get space shuttles out into space. Okay? We don't give them a huge kick and then let them glide away. Okay? We have thrusters that are continually pushing them out into space. Okay, so this wouldn't work. You would destroy mechanically anything on the object that's got this initial speed. That would be a boost or a boom right away. Instead, we apply energy so there's work done. Okay, anyway, but this is a great application of conservation of energy. So solving for VI, we get square root of 2gm over ri. And I just noticed I made the infamous mistake. I put a 2 there, a square there. Okay? This is a common mistake, and I did, I think, because I was just doing some force problems in the previous video. Okay? So remember, as I just caught myself, remember that potential energy is gmm over r, whereas force is gmm over r squared. Okay, so catch that. Make sure that's clear. Okay, so with that, we can now calculate what this initial speed is. And if you put in the numbers for the Earth, you'll get something around 11,000, 12,000 meters per second. Okay, that's booking it. It's really, really fast. Okay. All right, so let's go ahead and do it for this problem now. We say that the escape speed for planet X is 10,000 meters per second. Okay, and so that'd be Vx is square root of 2gmx over rx. All right, and we know this, but we don't know either of these. Okay, that's all right because we're just doing proportionality. Okay. So we have a planet Y, and we want to find Vy. Well, that's going to be 2gmy over ry. And we're told that they have the same radius, so ry equals rx. That's nice. But planet X is twice as dense. Okay. Now, if you think carefully about density, what we care about is mass, not density. But if the planet is twice as dense, then how does its mass compare? Well, because the radius is the same, that means the volume's the same. And therefore, since the mass is, or since the density is twice, the mass is just twice. Now, had the radii been different, we couldn't have done that. We'd have had to calculate mass as equaling density times volume. Volume is proportional to the radius cubed, and then we'd have to do all that proportionality. But thankfully, in this problem, the radii are the same, so the volume's the same. So doubling the density means doubling the mass. So we can now jump to that and say this is 2g2mx over rx. Okay, Ry equals Rx, My equals 2mx. Alright, that then just says that this is the same thing as square root of 2 times Vx. Everything else is the same, just pull out a square root of 2. Which, if you just plug in your numbers there, you can end up with 14,000 meters per second. Which is on par, it's a little bit bigger, which we'd expect since the mass is bigger and therefore it's got a stronger gravitational pull. Okay, now number 9 allows us to play with some of the other relationships we saw in the text. Okay, so we're told that the Jupiter is 300 times the mass of the Earth. We're told that the period of Jupiter is 11.9 years. Okay, whereas the period of the Earth is 1 year. Okay, that's the definition of the year. Now we're told that the radius of Jupiter's orbit is 5.2 times that of the orbit of the Earth. So that's the distance from the planet to the Sun. And suppose that the Earth were moved to the distance of Jupiter and placed in a circular orbit. So I'm emphasizing important words here. Okay. What is going to be the new period of the Earth? Okay, so the Earth is at Jupiter's orbital position, but the mass of the Earth. Okay, so how does that change the period of the orbit? Okay, again, you could just plug in the orbital equation, but it's so quickly taken from first principles that I'm going to start. We know that the only force acting on the object is gravity. So you have G, M, N, this would be the Sun, over R squared. And it's in a circular orbit, so that means that's equal to mv squared over R. We can cancel out the m's. Okay. We're trying to figure out what is the period, so we now need to find period. So we can see that b squared is equal to g m of the Sun over the orbital distance. Okay. But v, if it's a circle, is the same thing as 2 pi r over the period, and we're squaring that, so we get 4 pi squared r squared over the period squared equals g m of the Sun over the radius, and therefore solving for the period. We're going to say period, I'm going to go and square it, equals, take that up, take this down, we get 4 pi squared r cubed over g mass of the Sun. So again, this is something that you can memorize, but it's so quickly and conveniently related to first principles, foundational principles, that I really want you to see where it came about. All right, but with that, now that we look at that, the radius is the radius of Jupiter. Okay, and for Jupiter, it has a period of 11.9 years. So if the Earth is put out there, what's its period? What changes when we move the Earth out to Jupiter's radius? Well, notice there is no mass of Jupiter here. There's no mass of the Earth here. Way back here at this first principle step, the mass of the object orbiting canceled out. The only thing left was the body pulling them in orbit. So the Sun didn't change. None of the constants change. We're at the same radius as Jupiter. So the period is the same, which is cool. The period is purely a function of the radius, not of the size of the object rotating or orbiting. Okay, so very powerful principle there. Okay, let's move on to 10. Okay, this is another one to apply. Okay, so what we're told is that, this is kind of a cool problem, that satellites that are in really low near-Earth orbits, there is a slight drag because the atmosphere slowly dissipates to nothing out to space. So when you're close to the Earth, you're hitting some stuff. So you slowly, ever so slowly slow down, which means you're going to eventually spiral inward and burn up in the denser atmosphere that's closer to the Earth. So the question is, as you're moving inward, if you're going so slowly that you're still staying in circular orbits every time, so you're initially out here in your spiral, is just barely smaller. You know, it's just a really tight spiral coming inward. So you can see that, you know, they're pretty much circles the entire time. So if you stay in these circular orbits as you get smaller and smaller and smaller, are you slowing down, speeding up, or staying at the same speed? Now, the gut reaction, for me at least, is that you're slowing down. Obviously, you have a drag force. The drag force is slowing you down. Okay. Now, what happens is that you're being pushed into lower orbits, okay, which, if we recognize how the velocity is related for circular orbits, remember this is circular orbits, how velocity is related to the radius. As the radius gets smaller, the orbital speed gets bigger. So you're actually speeding up as you spiral inward. Okay. Now you can see this if you have one of those like a bowl and a marble, and you get a marble spinning around that bowl, and on the outer edge of the bowl it's spinning around. And then if you stop spinning it with adding energy, it will spiral inward, and it goes faster and faster and faster. Okay, because a similar principle applies there. Right. So the same principle applies here. But that's what's weird, is you're slowing because of drag, but you're actually speeding up because your radius is getting smaller. Okay, now that's only true if the drag force is small enough that you stay in circular orbits. Okay, so we applied that one to here. So you're speeding up. Okay, let's take a look at the exercises. 21. Okay, so 21, you're visiting a distant planet and you've made some measurements. Okay, so you know that the mass of the planet is twice that of the Earth, and the gravitational acceleration, or the free fall acceleration at the surface, is only 1/4 that of the Earth. Okay, so our question is, with just that much information, can you determine the planet's radius? Okay, so 21. Well, we know that the mass of this planet is equal to twice the mass of the Earth. We know that G of this planet is twice G of the Earth. So can we determine the radius of this planet? We know its mass. We know its gravitational free fall acceleration. Well, if we remember what G is, maybe we can. So think about that. Where's G? Now, G is equal to big G, the mass of the object, divided by the radius of the object squared. Okay? Sorry for my little squiggle there. Okay? Now, if that is equal to 1/4 G of the Earth, which we know is Gm of the Earth over R of the Earth squared, the G's cancel, and because I know m is twice the mass of the Earth, I can now solve for this unknown radius. I end up with 2me over r squared equals 1/4 me over re squared. So the mass of the Earth cancels there. And then solving for this re, you're going to get r squared is equal to 8re squared. It allows you to solve for r, and you're going to get 2 square root of 2 times re, or you're going to get 1.8 times 10 to the 7 meters. The radius of this planet. So again, it's boiling down to understanding, what does little g mean? Now part B says you're trying to escape the planet. So what minimum speed do you need to have? Well, that's the escape speed, which we have determined over here. We've already found that out. So since we've already done the legwork to show that, we can now plug that in. And if you do, you're going to get this escape speed, because we know G, we know the mass of the planet, twice the mass of the Earth, and we now know its radius, just plugging in our numbers. We'll end up with 9,410 meters per second. Okay. So because its mass is bigger, but its radius is also bigger by more than twice. The escape speed is smaller. Okay, moving on. Now we have 25. Okay, this is a fun one. So go read this one and really try and think about it. There's a lot of numbers given. We have a lot of different concepts that work together. Okay, so you are visiting a planet, and you've been able to measure its radius. So what things do we know? Okay, we know its radius of the planet. We know the period of rotation of the planet. I'm going to use a little t to emphasize that. All right. We know the orbital radius, which I'm going to put this. That's the orbital radius around its star. And we know the period of the orbit, which I'm going to put as big T. Okay. Utilizing some of the values we've already used, our traditional variables. All right. Then we also know G. We know all those things of this planet. All right. Now the question is what is the mass of the planet and the mass of the star? How do we find the mass of the planet? Okay. Well, here's a hint right here. Do we have enough information to find the mass of the planet? Yes, we do. We know G. We know the radius of the planet. We know big G, so we can find that mass. So solving for the mass in that one, we have G r squared over the big G. And if you plug in your numbers there, being careful that they give the diameter, but you need the radius, so divide that by 2. You get 1.5 times 10 to the 25th kilograms. Which seems reasonable. It's proportional. It's close to the mass of the Earth, so it seems like a reasonable mass. All right. Now the next question is, what is the mass of the star around which this planet orbits? Well, hint is right here. Can we find the mass of the star? Well, we know the period of rotation, the orbital period, and we know the radius of the orbit. We know the other constants, so yes, we can. So from that one, we can solve for the mass of the star in that case, and we're going to get 4 pi squared r cubed over gt squared. And the only kind of mathematical complication is this is given in days, so you need to multiply that number by the 86,400 seconds in a day. If you do, you'll get 5.22 times 10 to the 30 kilograms, which is on the same order as the mass of our sun. So it seems reasonable.